Hi everybody. In the past several videos, we've built up to more and more complex quantum systems, starting from model systems like the particle in a box and a harmonic oscillator, to hydrogenic atoms, to multi-electron atoms, to diatomic molecules, and finally we've arrived at sort of the culmination of our coverage of quantum mechanics, where we think about how these ideas can be translated to polyatomic molecules and their molecular orbital diagrams. As we saw for heteronuclear diatomic molecules, molecular orbital diagrams can be thought of as solutions to systems of equations, where we find an energy E and a set of coefficients C that refer to the atomic orbital coefficients within each molecular orbital. This idea can be generalized to any number of atoms, not just diatomic molecules. And to illustrate this, we're going to use a simple level of theory called Huckel theory to find the pi molecular orbitals and their energies of organic molecules. As a first example, we'll look at this molecule, 1,3-butadiene. And before we even get to the quantum mechanical picture of this molecule, I'd like you to think about these few questions from the perspective of the Lewis structure. In this molecule as a whole, how many valence orbitals are there? How many valence electrons are there? And which atomic orbitals interact to form the sigma system and pi system of molecular orbitals? I'll give you a few seconds to think about that, and I suggest hitting pause and taking as much time as you need. Okay, let's answer these questions one by one. To find the total number of valence orbitals, we can add together the valence orbitals on each atom. Each carbon atom has 4 valence orbitals, a 2s orbital and a set of 2p orbitals. And each hydrogen atom has 1 valence orbital, the 1s orbital. So if we add all those together, we have 4 carbon atoms, each of which has 4 valence orbitals, so that's 16, plus 6 hydrogen atoms, each of which has 1 valence orbital, that's another 6. 16 plus 6 is 22, which is the total number of valence orbitals. We can do the same thing for valence electrons, adding together the valence electrons from each atom. Each carbon atom brings 4 valence electrons, each hydrogen atom brings 1. 4 carbon atoms times 4 electrons is 16, plus 6 hydrogen atoms times 1 electron is 6. 16 plus 6 again is 22. So we have 22 valence orbitals with 22 valence electrons. And if you remember that every orbital holds 2 electrons, we know that that set of orbitals is half filled. So of those 22 total valence orbitals, we can now think about which of them form the sigma system and which of them form the pi system. In general, the sigma system consists of orbitals that are kind of pointing at each other. So those are all of the orbitals that exist in the plane of the molecule. For each carbon atom, that means it includes the s orbital and 2 of the 3p orbitals, the 2 that are in the plane of the screen. And for each hydrogen atom, that includes the 1s orbital. So the sigma system includes 3 orbitals from each carbon atom and 1 orbital from each hydrogen atom. So if there are 4 carbon atoms, and we're including 3 of those orbitals in the sigma system, that's 12, plus the 6 orbitals from the hydrogen atoms, that's 18 total. So there are 18 orbitals within this molecule that are part of the sigma system. And that only leaves 4 more orbitals. Each of the carbon atoms has an out-of-plane p orbital, a p orbital that's pointing in and out of the screen. And those 4 remaining orbitals form the pi system. So, to summarize what we just said, 1,3-butadiene has 22 valence orbitals, with a total of 22 valence electrons in them. And of those 22 valence orbitals, 18 of them interact to form a sigma system of molecular orbitals. If you were to run a full molecular orbital calculation of this molecule, you would find that those 18 orbitals are varying degrees of bonding and antibonding, and they all look different from each other. But for our purposes, we can basically think of that sigma system as being 9 sigma bonding orbitals that are low in energy and filled, and 9 sigma antibonding orbitals that are high in energy and empty. We're not really going to worry about them in detail. And the remaining 4 orbitals are the out-of-plane carbon 2p atomic orbitals, and those are going to interact to form 4 pi molecular orbitals. And as you've probably learned in organic chemistry, the pi system is really where the frontier orbitals are, the highest filled orbitals and the lowest empty orbitals. So if the 9 sigma bonding orbitals held 18 of the valence electrons, this pi system is going to hold the remaining 4. So this is really the part of the molecule that we're going to focus on. The 4 pi molecular orbitals that hold the 4 highest energy valence electrons. So we've introduced this molecule in kind of a lot of detail, but the result we arrived at is one that you can sort of take as given in the future. The idea that the out-of-plane p orbitals form the pi system, and that's where the frontier orbitals are. That's the part of the molecule that we really tend to think about the most. Okay, now we're ready to apply Huckel theory to the pi system of 1,3-butadiene. This equation at the top of the slide is basically the Schrödinger equation, H psi equals E psi, but where we've substituted in for psi a linear combination of the 4 atomic orbitals that are part of the pi system. We've labeled those 4 atomic orbitals A, B, C, and D on each of the 4 atoms, as was labeled in the previous slide, and the set of coefficients Ca through Cd represent the weight of each atomic orbital within the molecular orbitals that we're going to find. At this point, we're going to do something similar to what we did in the previous video for a heteronuclear diatomic molecule, and we're going to generate what are called the secular equations by taking the Schrödinger equation and multiplying it by each of the atomic orbitals and then integrating. So we can take this Schrödinger equation and generate 4 secular equations by multiplying by each of the atomic orbitals in succession, A, B, C, and D. I've animated those 4 equations into the slide, and as you can see, they look pretty complicated. I suggest you take a little bit of time to stare at them, but basically each line represents the Schrödinger equation front multiplied by one of the atomic orbitals. The first line represents multiplication by orbital A, and then integrated, and then distributed into different terms. Those 4 lines represent the 4 equations that you get by multiplying by A, multiplying by B, multiplying by C, and multiplying by D. It would be really difficult to solve these equations exactly, because they have a lot of integrals that integrate orbitals over all space. They include a Hamiltonian operator that has a lot of terms that we haven't written out. But in Huckel theory, we can make some big approximations to find the values of these integrals. The Huckel approximations are shown here, and we'll look at them one by one. The first approximation is that the overlap integrals are equal to 0. Recall that the overlap integrals are the integrals that have the form integral of one orbital times another orbital over all space. So something like integral of A times B is an overlap integral. So because we're assuming those are equal to 0, we can ignore a lot of the terms in these equations. I should point out that this is a fairly drastic approximation to assume that the overlap integrals are 0. In reality, they're not. But it turns out that we're going to retain the information about the interactions between the orbitals in the resonance integrals later on. So if we're just looking for a qualitative picture, it turns out to be okay to assume that the overlap integrals are equal to 0. The next approximation is that the Coulomb integrals are equal to alpha. This is something that we saw in the previous video. Integrals of the form integral of an orbital times the Hamiltonian operator applied to the same orbital. So something like integral of AHA. Those terms are going to be equal to alpha. So you can see a few of those terms here, integral of AHA, BHB, CHC, and DHD, and we're going to assume that all of those are equal to the same alpha, which is essentially an approximation for the atomic orbital energy of each of those atomic orbitals. Finally, we're going to make an approximation about the resonance integrals. Remember, the resonance integrals are the ones that are integral of an orbital times Hamiltonian operator applied to another orbital, so something like integral of AHB. Those integrals basically tell us how much a pair of atomic orbitals interact. So it makes sense that 2 atomic orbitals that are close together in space would interact more than a pair of atomic orbitals that are far away from each other in space. We're going to make another kind of drastic approximation here, that if a pair of atomic orbitals are nearest neighbors, their resonance integral is equal to some number beta, but if they're farther away from each other than that, their resonance integral is equal to 0. So based on the linear shape of our 1,3-butadiene molecule, some of those resonance integrals are equal to beta, and some of them are equal to 0. And finally, the only integrals that we haven't talked about yet are the ones on the right side of these equations, the integral of a squared, the integral of b squared, etc. And those are just normalization integrals. So if we assume that our atomic orbitals are normalized, we can say that all of those are equal to 1. So now we've taken this system of equations, and rather than having a bunch of integrals that are difficult to calculate, we've made some big approximations and assigned numbers to all of them. This leaves us with a pretty reasonable looking system of equations, and while it would still be annoying to solve them by hand, you can imagine that a computer could solve these pretty easily. Linear algebra is definitely not a prerequisite for this course, but I suspect some of you have taken linear algebra, and if you have, you may recognize that a system of equations like this could be written as a matrix multiplication equation. So if this form of the system of equations looks familiar to you, great. If it doesn't, don't worry about it. We'll talk about everything we need to know. What we have here is a 4x4 matrix, the Huckel Hamiltonian matrix, that has all the alphas, betas, and zeros that we talked about, multiplied by a column vector with Ca, Cb, Cc, and Cd, the atomic orbital coefficients. And that matrix times that vector is equal to a constant E, the molecular orbital energy, times the same column vector of coefficients C. Whether or not this form of the equation looks familiar to you, you can see it as basically an operator, in this case a matrix, times a function, in this case a column vector, equal to a constant times the same function. And we've seen that form of equation before. That's an eigenvalue problem, the same way that we've seen throughout quantum mechanics. In this case, the eigenfunctions, the eigenvectors, are the atomic orbital coefficients, and the eigenvalue E is the molecular orbital energy. Using computer software like Mathematica, it's fairly easy to put in a matrix and find the eigenvalues E and eigenvectors, the sets of coefficients C. So again, linear algebra is not a prerequisite for this course, so we won't focus on this step, and I will basically give you the answers. I'll show you what the eigenvalues and eigenvectors are for this molecule, 1,3-butadiene. This involved the interactions of 4 atomic orbitals, so we expect there to be 4 molecular orbitals, and these 4 equations represent the 4 molecular orbitals. In each case, we have the Huckel Hamiltonian matrix H multiplied by a column vector equal to a constant involving alpha and beta times the same column vector. And by interpreting these 4 eigenvalue equations, we can draw and understand the pi molecular orbital diagram of 1,3-butadiene and sketch pictures of the orbitals. Before drawing the MO diagram, I'd just like to say a few things about interpreting these equations. First of all, remember that the eigenvalues, the constants involving alpha and beta, these are the molecular orbital energies. So all of these molecular orbital energies are alpha plus or minus some multiple of beta. Also remember that, as was the case in the previous video, beta is negative. So the lowest energy orbital is actually the one that is alpha plus the highest multiple of beta. And then the eigenvectors, the sets of atomic orbital coefficients, those show us what the molecular orbitals look like. When you see numbers that have higher absolute values, that means the weight of the molecular orbital on that atomic orbital is the largest. We sometimes draw that as having sort of larger lobes within a molecular orbital. And then when you see positive and negative signs, that represents the positive and negative signs of the wave function, when you see shaded or unshaded parts of the orbitals, or blue and green parts of the orbitals, depending on how the pictures are drawn. Okay, so now we're ready to take these equations and translate them into pictures, and we're going to do that one by one. So first we'll start with this lowest energy orbital. You can see that its energy is alpha plus 1.62 beta, and that the sign of the orbital is positive all the way across the molecule, and that it has the most weight on atoms 2 and 3. So if we translate that into pictures, it looks like this. The energy is alpha plus 1.62 beta. We draw larger lobes in the middle of the molecule because the weights were larger, and we have blue lobes sticking out at us on each atom because the sign was the same across the entire molecule. So this should make sense when you see that the lowest energy pi orbital is the one that's fully bonding, the one where the sign is the same across the entire molecule. I suggest that you take your time and look carefully at the equations on the previous slide and draw this molecular orbital diagram for yourself, but I'll just animate the rest of the orbitals in. They look like this. You can see that the energies get higher as you go from alpha plus some number beta to alpha minus some number beta. And you can see that as you move from bottom to top here, you have orbitals that are fully bonding at the lowest energies, and an orbital that's fully anti-bonding at the highest energy. In other words, as we've seen throughout the previous videos, more nodes typically means higher energy. That's true whether we're talking about atoms or whether we're talking about molecules. And finally, the last thing we'll do to complete this molecular orbital diagram is to fill in the electrons. We said that this pi system has 4 electrons. We could either figure that out by counting up all of the electrons in the molecule, or just by looking at the Lewis structure and seeing that there are 2 pi bonds in there, which means there are 4 pi electrons. So, as we always do, we fill them from bottom to top according to the Aufbau principle. And here we go. We've completed our pi molecular orbital diagram of 1,3-butadiene using Huckel theory. Just a couple of takeaway messages here. One thing that's interesting is that the pi molecular orbitals that we came out with actually kind of resemble particle-in-a-box wave functions. So remember, the 4 lowest energy wave functions of a particle in a box look like waves with increasing numbers of nodes. 0 nodes, 1 node, 2 nodes, 3 nodes. What we have here in our 4 pi molecular orbitals is something that looks kind of like that, but drawn from the perspective of linear combinations of atomic orbitals. But if you kind of squint, those 4 molecular orbitals do sort of look like waves, with 0 nodes, 1 node, 2 nodes, and 3 nodes. The other thing I want to point out is that even though we've taken a lot more time to draw this MO diagram than it takes to draw Lewis structure, it does have a certain similarity to the Lewis structure. Remember, the Lewis structure of 1,3-butadiene shows double bonds at both ends of the molecule. And in this case, when you look at where the pi electrons are, if you look at the highest occupied molecular orbital, it does have a bonding interaction between atoms 1 and 2, and a bonding interaction between atoms 3 and 4. So in a very approximate sense, the Lewis structure was telling us where the strongest bonds in the molecule are. It's possible to build up a similar picture of the pi system of other organic molecules, and you'll get more chances to do this, but I just wanted to briefly mention the example of benzene. Again, we can start by thinking of the Lewis structure of benzene and thinking about how many pi orbitals there are and how many pi electrons there are. We'll go quicker this time. Again, the pi system consists of the out-of-plane carbon 2p orbitals. So we have 6 carbon atoms, each one has an out-of-plane p orbital. So we have 6 atomic orbitals that interact to form pi orbitals. And we can see from the Lewis structure that there are 3 pi bonds. So that means there are 6 pi electrons. If we want to apply Huckel theory to benzene, the first step is to write out the Huckel Hamiltonian matrix. In this case, since we're looking at the interactions of 6 atomic orbitals, it's a 6 by 6 matrix. And after a little practice, you'll be able to write these matrices pretty quickly. Notice first of all that along the diagonal from top left to bottom right, the entries are always going to be alpha. Those are the Coulomb integrals representing the atomic orbital energy of each of the 6 atomic orbitals. And then off the diagonal, all of the entries consist of betas and zeros. Those are the resonance integrals. And remember, they're beta if 2 atomic orbitals are nearest neighbors, and they're 0 if 2 atomic orbitals are farther apart from each other. So for example, if you look at row 1, column 2 of the matrix, that's a beta, because orbitals 1 and 2 are nearest neighbors. But if you look at row 1, column 3, that entry is a 0, because orbitals 1 and 3 are farther apart from each other. They're not nearest neighbors. So you can just fill in all of the off-diagonal elements as beta and 0, looking at whether 2 atomic orbitals are nearest neighbors with each other. The next step is to find the eigenvalues and eigenvectors of that matrix. Again, because not all of us have taken linear algebra, we're not actually going to focus on that step in this course. We're going to assume that the eigenvalues and eigenvectors will be given to you, as they are on the bottom of this slide. Since we had 6 atomic orbitals interacting, we now have 6 eigenvalue equations telling us the energies and character of all 6 pi molecular orbitals. We won't go through the whole exercise again of translating these equations to a molecular orbital diagram, but I definitely suggest that you do it on your own, looking at those equations and remembering that the eigenvalues, those constants with alpha and beta, those are the molecular orbital energies, and then the column vectors that have coefficients C1 through C6. Those are the coefficients of each atomic orbital within each molecular orbital. They tell you the weight and sign of the orbital on each atom. And before ending this video, I just want to put all of this in a little bit of historical context. Huckel theory was devised in 1930, which is before electronic computers existed. So this is a really early attempt to describe the molecular orbitals of organic molecules. And as a result, it's very approximate, and it can only handle certain systems, specifically the types of pi systems that we've been looking at in this video. Huckel theory is really good for qualitative understanding of the appearance and relative energies of the orbitals, so it does a good job telling you sort of which orbitals are lowest in energy, which are highest in energy, and what each of them look like in terms of symmetry. But it does a pretty lousy job for quantitative results. It doesn't give you numbers. There are many more modern updates to the approach that's used in Huckel theory that use computers to actually calculate the overlap integrals and the terms that we just approximated in Huckel theory. And those methods can handle not only pi systems, but full molecular orbital diagrams of any molecule that you're interested in. And finally, just a few takeaway messages from the last several videos, which have built up molecular orbital theory. MO theory is based in quantum mechanics, so it gives us a more detailed understanding of electronic structure than valence bond theory. And by valence bond theory, I mean Lewis structures and resonance forms and things like that. MO theory is more detailed than that. Modern methods in computational chemistry, or at least computational quantum chemistry, are rooted in molecular orbital theory. They are all in some sense trying to solve the Schrödinger equation, though every method relies on different approximations. But I don't mean to imply that valence bond theory is in some way bad. It's always very valuable to draw Lewis structures to quickly gain insight into where the electrons are in a molecule, and how many bonds there are, and how many valence electrons there are, and things like that. So it's sort of a trade-off, where valence bond theory gives us less detailed information, but we can often think about things more quickly and more intuitively. But molecular orbital theory gives us the more quantitative picture and the more quantum mechanically accurate picture. That's all for now, and really that represents the end of the quantum mechanics coverage in this course.